Welcome to another Syvecs help video. On this particular video we're going to look at the nitrous control on the Syvecs range of ECUs. The nitrous control on the Syvecs range of ECUs can be done in two manners. We can do it in a dry system where the fueling is done via the ECU, or via a wet system where you drive the fuel and the nitrous solenoids through the ECU, and the duty is set as the same. They're a mirrored duty output to both solenoids, and it's down to the customer to ensure that the actual fuel jet and the nitrous jet are matched pair. So the way that you first go about this in nitrous control is you need to first go down to the I/O configuration and under pin assignments to see how the solenoids can be wired in, etc. So once you've wired them into your desired output, you can actually then set up how you'd want it to be controlled. Now the first thing to note is that on the S8 ECU, the ignition output drivers can handle up to 25 amps, which is generally good enough for most of the so the Wizard of Nitrous solenoids, or the newer type solenoids, which generally don't pull more than 20 amps. They can drive those actually direct from the ECU fine. If you're running an S6, the maximum ampage output on those is through the injector outputs, and they can only handle 10 amps max. So we tend to generally recommend to use a solid state relay on the use of an S6. Now first of all, if you're going to use a wet system, you would define the outputs under the nitrous output control, so that nitrous A and B would be on the outputs you're using for the solenoids, and they're basically two mirrored outputs. So the duty that's applied to, say, nitrous control A will be mirrored on all the other outputs, and that's the same on the S6 and the S8. So if you're using a wet system, then you'd go about doing it so that both of the solenoids are wired in and onto control A and B, so that they're mirrored, and the actual pulse width that goes out to both the solenoids are the same, and it's down to you to make sure the jets are right. So when you're in the outputs, you can see the nitrous control here, 4 on the S8, 2 on the S6. Here you can go in to the actual the configuration tree and actually set what output you want it to be used on. Once you select that, the main thing to remember is that once you've set these is to ensure that you program the ECU to make sure those are saved. Okay, it's worth just going over the nitrous control actual strategy first in the actual main part of the actual SCAL code, to ensure that all the settings you've got are right, so that you're not suddenly going to program it and then find that you're suddenly going to start pulsing and adding more fuel, etc. It's worth also noting that make sure that no nitrous is applied to any of the system until you've actually fully tested using the output testing on the particular outputs to ensure that they are pulsing correctly, the solenoids, and working right. So once you've done that, you can also then define a nitrous control switch under the inputs. So you can see here the nitrous control switch, you can define that to a certain input. If you don't want to use up the I/O for an input for the nitrous switch, then you can define this via the calibration switch. So certain calibration switch positions actually have the nitrous on, and select different nitrous tables, etc. Also, it's worth noting that you can actually monitor nitrous bottle pressure on the Syvecs range of ECUs, and you can actually then, under the outputs, define the nitrous bottle heater. So what you can actually do is under outputs, you can go up to here, go to output functions, you've got your nitrous bottle heater. What you can do is you can set a minimum nitrous bottle pressure, so the actual heater turns on above this pressure, and then what you can do is you can say you want the heater on when it's below 870 psi, and the heater goes off when it's above 900 psi. Okay, these obviously can be used to suit, and you generally we just go for a relay on the bottle heater because they generally tend to pull a few amps. Okay, so what we're going to do now is go up to the nitrous control area. When you're in nitrous control, the first thing you'll see at the top of the list is the PWM frequency. On your solenoids that you're generally using, you should actually have from the manufacturer PWM frequency, which the solenoids work best at. Generally they're around about, say, 15 to 30 hertz. So you define that in here and set that up. You then got your engine speed breakpoint, so you can define on all your tables what the engine speed breakpoints will be. So if the engine, say, revs to more than 9,500, you can actually change that and define on here. Same for the throttle position breakpoint and the manifold pressure breakpoints. Depending on how you actually set up the nitrous control to work, or based on the primary load which you're using for the actual nitrous strategy. So under your base demand select, you can select it so your load is either on throttle position or manifold pressure, and that sets up your tables and so forth. You've got your nitrous pressure breakpoints for obviously your trims, etc., and the vehicle speed breakpoints as well, so you can define an actual change the amount of nitrous based on vehicle speed if you wish as well. You can also actually, in the latest launch firmware, actually make changes to the nitrous control after the launch. You have an exit timer, so for a set timer amount you can actually change the amount of nitrous being applied to help with countering any traction issues, and obviously on the launch you sometimes don't want full-blown amount of nitrous. So once you've defined all these and set the base demand select as you wish, you have got then your base duty tables. This is where it allows you to actually define the amount of the duty that's being applied to the solenoids. So here you can see at the moment it's based on TPS, but if we wanted to change that to say for a turbocharged car for manifold pressure, you can do that there, and then you'll see the actual tables are based on manifold pressure. It's quite useful to do this because you can actually use the nitrous control system as like a turbo spooler. So below a certain manifold pressure you can actually have it so that, say, the nitrous comes in at 100% and actually helps spool the turbo, and then if your target manifold pressure is, say, 1.5 bar, you could actually bleed it in so that the nitrous actually helps it spool up and actually help to get the turbo and the actual engine generating a lot of turbine pressure to actually get the turbo up on full boost earlier. But either way, you can define this based on your RPM, and this is down to the calibrator's setup, how much power you would wish to have on different maps. So you've got 4 base duty maps, and these you can flip between onto the calibration switch under nitrous control. So you can come into here, and on particular calibration switches you can define which base map is used, either cal 1 to 3 or whether it's off. Once you've set these up as you wish, you then got a duty multiplier then for TPS. So if you're using the manifold pressure as the axis on the base duty tables, then the duty multiplier would be based on TPS. Vice versa, if you did it on TPS, then this would be manifold pressure. This is quite useful to have so that you can obviously, based on different throttle angles and the airflow change across the actual throttle plate, you can change the amount of duty being applied to the nitrous to ensure that the power delivery is as best it can be. You then got a duty multiplier for barometric pressure and a duty multiplier for vehicle speed. This is quite a useful one to be able to create a ramping effect of the power. So based on your vehicle speed you can actually define how much nitrous is actually put in at different points. You can change the breakpoints for this table further down, at the top under the vehicle speed breakpoints. Okay. Once you've set those up, obviously it's quite a nice way to be able to ramp in the power. You then got the enable throttle position, in which point the actual nitrous control works or turns on and the actual duty starts getting applied based on your tables. So you can, generally you want this to be more than 25%, but this is down to the actual tuner to set. You then got the enable engine speed, so you can actually define it so that when over the actual certain engine speed the nitrous control kicks in as well. You then got the maximum rate of duty increase. This is basically a calibration which allows you to select over a second how fast the actual rate of duty is increased. So over 1 second at the moment, you can see on here we've got 200% per second, which is generally a good starting point. Obviously if you want it to be so the duty is ramped in slower, then you could lower this down so that it would be only, say, 100% duty per over a second. So for example, the way it's set at the moment, at every half a second it's adding in 100% duty. Okay. Obviously you can lower this right down if you want it so you don't have nitrous coming in straight away, but on this particular car it was a small jet, so we wanted it coming in as soon as possible. You've then got the PWM battery adder based on the actual battery voltage on the ECU. Different solenoids, some solenoids will be able to give you this information, others you'll need to do it on the test bench. If you don't have the information, then you can consult the actual solenoid to make sure that is right. Once you've got that set up, you can define it based on different battery voltages. Obviously you need to apply more duty at different battery voltages to the actual solenoids to make sure that the actual amount of flow is the same. You then got the fuel adder base engine speed. Now if you're using the dry system of the nitrous control, here you can actually define the engine speed in which you do your fuel calculations to work out how much fuel is going to be implemented on the dry system. Okay, now to actually help out with this, I've actually created a little math calculation here, which will pop up in a sec on the screen. You then obviously got the fuel adder tuning based on your RPM, so based on different engine RPMs, you can actually change the fuel stuff that's going on through the dry nitrous system to actually help out making sure the fueling is actually 100%. And you can also do the same again for manifold pressure and for the nitrous bottle pressure, which is quite important. It's very useful to have that set up and have the nitrous bottle pressure monitored on a dry system, especially to ensure that the fueling is always 100% perfect. You can then change your ignition timing that's being run based on your nitrous, the actual duty being applied. So based on the nitrous base, you can actually change your ignition timing so that you can pull timing out or add timing based on the amount of nitrous you're actually deploying into the engine. You then got the maximum rate of ignition adder increase, so based over a second you can define how much ignition changes occur. So once you've done all that, the good thing to look at then obviously is under Nitrous Control, just to go back over it again, you can actually have it so you have different duty multipliers per gear and per calibration switch, which is quite useful. And you can also have it so you can turn the bottle heater to enable on different positions of the cowl switch. Any further questions on the nitrous control system, then don't hesitate to ask the Syvecs help team. Either speak to pat@syvecs.co.uk or ryan@syvecs.co.uk. Hope this has been helpful, and good luck.